Welcome back, everybody. So remember yesterday we were talking about that idea of having rigid transformations, right? Rigid transformation. A rigid transformation is one that preserves congruency, one that keeps the size and shape of the figure the same, only distorts the orientation or position, right? So today, or yesterday, those were all rigid transformations. Today, what we're going to talk about are the non-rigid transformations, ones that actually change the size or shape of the figure. Okay, it'll kind of distort it to anything. Anything you want to make it look like, we can do that. All right. So, okay, imagine, if you will, grasping 2 points on the graph of a function that lie on opposite sides of the y-axis. Okay, so say you had some function, I don't know what it looks like, but some function, and you take the y-axis, right? And you take either point on either side of the y-axis, and you start pulling those points away from the y-axis. Okay? I'm not stretching it like all around, I'm just pulling away from the y-axis, just stretching it out this way. That is what's called a horizontal stretch of the graph. If you push the points toward the y-axis, that would be what's called a horizontal compression. Okay? We can have both vertical and horizontal stretches and compressions. Now, they all deal with a particular axis. Okay? You're either stretching or compressing toward the x or y axis, or stretch or compressing toward the x-axis or y-axis, obviously, right? Now, stretches and compressions are not congruent to the original graph, right? We have to get that in our brains. It is not going to look the same anymore. It's going to look generally similar, but it's not going to look the same anymore. Where shifting around preserve congruency, stretches and compressions do not. Okay, so let's talk about them one by one here. I've got the horizontal stuff. Let's do the horizontal stuff first. Okay. Again, key things that I want to point out to you. I would like you to write out what changes, and then this little rule that we've got going on there. Okay, so do that for each one of them. I'm not going to box each one of them, but do that for each one of them. So let's look at the horizontal stuff. Notice that the horizontal stuff is pulling or pushing toward or away from the y-axis. Okay, again, the horizontal stuff is pushing or pulling from the from the x. Oh, excuse me, I said it right. The y-axis, right? The y-axis, which is going to force the x-coordinate to change. The x-coordinate of the graph is going to change. Okay, each point is pulled or pushed toward or away from the y-axis, which means the x-coordinate is going to change. Now, how is it going to change? It's going to turn from x comma y into bx comma y. So this is where we start multiplying. This is where we take a scale factor and multiply to that value of x. I'm changing the x value. Now, it depends whether that number is a number greater than 1 or a number less than 1. Okay? If the number is greater than 1, it's going to turn into a stretch. If the number is less than 1, then it's going to turn into a compression. Okay? Special note there. Why am I only talking about the absolute value of b? Why do I make note of saying the absolute value of b? Can you tell me? Brainstorm why. It's always dependent upon the value of b. What do you think? Not the, so what does absolute value disregard? Like what does absolute value take care of? The negatives, right? The absolute value means, I'm just talking about the value of the number. So the function absolute value just says, okay, don't worry about any negatives. Why don't I have to worry about negatives here? Like what about a compression of like -3? Like wouldn't that make it really small? No, not necessarily. That's actually a stretch. Okay, -3 would be a stretch. What's a negative do? What's a negative do? No, let's make it go left. What's a negative do? A negative multiplied. You're thinking adding or subtracting, right? A negative multiplied. We learned this yesterday. What is a negative multiplied to a? It's a reflection. It flips it, doesn't it? right? So I'm talking about the absolute value because the negative or positive about it doesn't really matter. The only thing a negative does is flips it across an axis, whether I'm talking about multiplying the x to the y value, right? Okay, the only thing a negative does is takes a reflection. Right? So that being said, if I've got a stretch by 3 or a stretch by -3, those are technically the same amount of stretch. Right? One is just reflected and the other is not. Okay, I'm stretched to the exact same amount. One is just reflected and one is not. Okay, so vertical, obviously, then I would push or pull away from the x-axis, which would change the y-coordinate. Okay, the y-coordinate changes, and it goes from x comma y to x comma ay. Again, these letters A and B are going to be similar throughout the year. If we're talking about transformations and I say what's the A value, I'm referencing a vertical stretch or compression. If we're talking about transformations and I say what's the B value, I'm talking about some sort of horizontal stretch or compression. X comma y is going to map to x comma ay. Notice that in a horizontal stretch or compression, the y value stays the same. In a vertical stretch or compression, the x value stays the same. So just make sure that you pay attention to what you're multiplying. And again, this is multiplying, right? I'm multiplying by some sort of scale factor to make it stretch or compress. The same rule applies for the fraction piece, between 0 and 1. That would, if I'm multiplying a number less than 1, that would mean it's going to be a compression, a vertical compression. If it's a number greater than 1, it's going to be a vertical stretch. And again, you got to visualize it, so you've got some function. And if it's something vertical, I'm going to take points on either side of the x-axis, and I'm either going to stretch them apart or push them back together, right? Stretch them apart, push them back together. Okay, so let's try it here. Use a table to perform a horizontal stretch of the function y equals f of x by a factor of 3. Graph the function and the transformation on the same coordinate plane. So let's do this one here. This is the same one you just said, right? Horizontal stretch by 3. Okay. Horizontal stretch by 3 is going to map x comma y to what? Let's start there. Let's start there before we pick off our points. What is it going to map to? What coordinate is going to change for anything horizontal? The x coordinate. And it's going to be stretched by 3. So it's going to be 3x comma y. Okay, so the same thing that we did yesterday. Let's pick off any critical points. Looks like I have a change. Well, let's say that actually crosses the origin point there. Okay, let's say 0, 0, and here's a change in direction as well. Notice that it curves between those 2 points. Let's pick off this point here, and let's choose one more. Let's go right there. Okay, so I've got 4 coordinates there. The first one being -1 comma 3. The second one being 0, 0. Third is 2, 2. And fourth is 4, 2. Okay, so now this is going to turn into -3 comma 3. 0 comma 0. Notice that the origin point didn't change. 6 comma 2. 12 comma 2. That's going to be kind of hard to graph. Okay, so let's graph these points. I've got -3 comma 3. I've got 0 comma 0. I've got 6 comma 2. And then I've got 12 comma 2. Okay, here we go. Here's some estimation going on here. 7, 8, okay. 7, 8, 9, 10, 11, 12. Sure. 12 comma 2. Sure, somewhere around there. Do the best you can on you're there. It's a straight line between these 2 left points. It's a curve up to the next one. And then it's a horizontal line over to the next one. Did it truly horizontally stretch this out? Yes. Always be able to visualize what should have happened. By the end of the year, actually soon when we start getting into transformations of specific functions, like when we get to the end of transformations of linear functions, I should be able to tell you exactly what transformation is going to happen, and you should be able to visualize it. And also, I should be able to give you an equation, and you should be able to visualize it. That's not so hard with linear ones because you work with them a lot. But if I give you a quadratic and you just look at the equation, you should be able to visualize it without even needing to graph it. Based on these transformations. Vertical compression by a factor of 1/2. Vertical compression by a factor of 1/2. Why don't you guys do this one? I'll give you a second or two here. I'm going to pick off these points for us all here. Looks like here's a good point. Here's a good point. Let's choose that one. And let's assume that it's going to cross nicely right there as well. Okay, let's start up here. Looks like we got x comma y, map to, ooh, that's a really long arrow. -5 comma 1. We got -3 comma -2. We got -2 comma 0. 1 comma 1. All right, so I'm going to take x, y, and I'm going to map it to x comma 1/2 y, right? X comma 1/2 y. So that means I'm going to have -5 comma 1/2. I'm going to have -3 comma -1. I'm going to have -2 comma 0, and I'm going to have 1 comma 1/2. Okay, so that means we got, now again, you should try to visualize what's going to happen before you regraph it. It's always a good idea to try to think about, okay, what should happen? Vertical compression down toward the x-axis, right? Okay, so let's see if that actually worked. -5 comma 1/2, -3 comma -1, -2 comma 0, 1 comma 1/2. Okay, line in here, here, here. There we go. Did it actually vertically compress? Yeah, in my mind, it definitely did. Okay. Let me ask you this question. What is the only coordinate that did not change? -2, 0. What's that point called? The x-intercept. So what I'm saying to you is a vertical structure compression will not change the x-intercept. A vertical structure compression will not change the x-intercept. What won't change when I do a horizontal structure compression? The y-intercept, right? Because I'm changing the, with a vertical compression, I'm changing just the y value. So if the y value is 0, it will never change. Okay. These special points, the intercepts, are going to be key in when we start transforming more difficult functions. Okay, the graph shows the cost of painting based on the number of cans of paint used. Sketch a graph to represent the cost of a can of paint doubling and identify the transformation. Okay, so I see the graph on here, you see the graph on here. Let's sketch it right on that original graph. Okay, we're going to sketch the cost of the paint doubling. Okay, the cost of paint doubling. So we're going to right away, let's pick off some points here. X comma y is going to map to, well, what does it mean when I say the cost of the paint doubles? Which value is changing? Am I changing the X value or am I changing the Y value? I'm changing the Y value, right? I'm taking the X value is going to stay the same, but the Y value is going to become 2 times whatever it was. It's going to double, right? Right there, what is my transformation? It didn't tell me within the problem. What is my transformation? How do I identify what that is? What is it? Candle? It's not going to be a compression.
Horizontal stretch.
Not horizontal. Do I change the X value? No, I'm only changing the Y value, right? So it's going to be something vertical. Vertical stretch by 2. V stretch by 2. Whenever you identify what a transformation is, not only tell me direction, vertical or horizontal, not only tell me what it is, stretch, compression, shift, I don't know, but also tell me of magnitude. Tell me the number as well. Vertical stretch by 2, okay? So let's pick off a couple points. I think the easiest point to pick off is 0, 0. And let's just pick off one more. It's just a line, right? So let's say 3, 150. We only need 2 because it's just a line. Now, let's graph this. Or sorry, let's actually transform it now. 0, 0 stays 0, 0. 3, 150 becomes 3, 300. All right, now I take 0, 0, and then 3, 300. And there's my line. Now, we said that this was going to be a vertical stretch. Does anyone see when they graph? Couldn't this also look like a horizontal compression? Like, doesn't that look the same? Right? I'm just talking about the look of the graph. I know we know better based on the problem. I know that. But if I just looked at the graph, can I tell apart a horizontal compression to a vertical stretch? No, I can't. Okay? I know better because I know the context of the problem. I know I wanted the cost to double. Cost was the dependent variable, the Y value. So I'm stretching out the Y values, right? But wouldn't it also be the same to say that if I bought 6 cans of paint with the old price, it was $300. But now if I buy 3 cans of paint, it's $300, right? So that same thing happened where I compressed the Y value, or excuse me, compressed the X value, right? Horizontal compression. But because we know the context of the problem told me I wanted to double my paint cost, that we know better. We know that it's a vertical stretch rather than a horizontal compression. Okay. Linear functions are weird like that. Okay. Once we get past linear, it's very easy to tell the difference between a horizontal and vertical stretch and compression. But linear ones are weird because they're just straight lines. There's not much to it. Okay. All right. Let's take a look at one more. Suppose that a discounted rate is 3/4 of the original rate. Sketch the graph to represent the situation. Identify the transformation of the original graph. Okay, so it's not really, oops, that's a marker. It's not really giving us too much information within the context of the problem there. Make it a little bit smaller here for us so I can put it all on one screen. But looking at the graph, it looks like I've got obviously recording studio fees. The dependent variable is the actual fee. The time is my independent variable, my H value, X value along the X-axis. Okay, but it says, okay, suppose that a discounted rate is 3/4 of the original rate. 3/4 of the original rate. So what's going to change? When I set up my table here, X comma Y is going to map to what? Well, is the time changing? No, the rate is changing, right? Oh, excuse me, the discount, the fee is changing, the fee is changing, right? It's 3/4 of the amount. So what's changing again? Is it the X value or the Y value? The Y value yet again. X comma 3/4 Y. So what is this again? Well, it's a stretch. It's actually, this one is a compression, but it's still vertical, right? It's still vertical. I'm changing the y value. So now I'm going to say vertical compression by 3/4. Okay. Not only give me direction, give me what it is, and by magnitude. All right, so again, if it's linear, heck, let's pick out 0, 0. That's going to be an easy one. 0, 0. This looks like a direct variation, and that's not going to change at all. Okay, let's pick a nice and easy point. What's one that I could easily take 3/4 of? Let's go way out there. Let's go, heck, let's go 10, 300. Go crazy, folks. It's Friday. Woohoo! All right, 300. 3/4 of, I can do this in my head here. 3/4 of 300. Well, that would be 900 divided by 4. $225. Okay, 10, 225. Wait, is that right?
Yeah.
I know, because I multiplied by 3. 3/4. 300 times 3/4. Okay. Yeah, because 1/4 would be 7. All right, so there's my new coordinate. So let's graph it. 0, 0, and then 10, 225. Oh, somewhere about right there. Okay, here we go. No. Hey, that's pretty good. There's my new graph. And this is a vertical compression by 3/4. All right. Sound good? So now we know all the different types of transformations that we could possibly have. You've learned them all now. So what we can do now is eventually when we get to it, when we start learning each new function, we're going to, stretch, compress, shift, reflect, quadratic, and then polynomial, then rational, and then so on and so forth. Okay. All right. Let me stop the video and we can pull up the homework for you guys.